Hello, I'm Marion. I'm part of the optical scattering measurement department at Synopsys, and today we are going to talk about retroreflective sample measurements with OSG instrument solution for LIDAR application. So first, the agenda. We are going to start with a short presentation of our laboratory, what do we measure, how we measure it, and a quick summary of our product. Then we'll go to the core of the subject with the presentation of the principle of retroreflection. What is it? Where can we find it? And why is it interesting? And is it a challenge to measure it? This will lead us to the presentation of our product, MiniDiff V2, with a description and some technical specification. Then we will finish by the presentation of some measurement examples. So first, our lab, which is based in Hyères in France. We are equipped with a photometric laboratory in a dark room, which includes a high specular bench, goniomphotometer reflex, video photometer, lux meter, luminance meter, spectrophotometer, different integrating sphere with different size for visible or for infrared, and refractometer. In this lab, temperature and humidity are controlled and regulated to ensure an optimal measurement environment. The class of our laboratory is 10,000, but we also have a clean room with 100 class. So what do we measure in our lab? We are principally interested in BSDF measurement, but what is it? As you already know, when you light a surface, the surface captures the light in many directions. In fact, we collect and characterize how the light is scattered from any surface via the measurement of a quality named BSDF, for bidirectional scattering distribution function. You will see BRDF when you work in the reflected space and BTDF when you work in the transmitted space. The definition is here. It corresponds to the ratio between the luminance on the sample surface at observer direction to the luminance on the sample surface from the source direction. The unit is the steradian minus 1. Here, just two examples of BSDF measurement for two classical samples. The first one here is a Lambertian sample with which scattered the light in the same way in every direction. You have here the BSDF map, and you can see that it, of course, captures the light in the same way in every direction. Here you have the 2D representation with the BRDF in function of the scattering angle, and you can see that the curve is flat. The second example here is a perfect mirror, where you can see that the curve, the scattering curve is direct. How can we measure BSDF? It exists two principal ways. The first one here with gonio-photometer, where a light source illuminates a sample. The sample scatters the light in many directions, and you have a mobile detector which turns around the sample to collect the scattered light. It can be the opposite with a fixed detector and a mobile light source. The other way is a system based on camera with a system of lens which permit to collect the scattered lights and send it to the camera. We are equipped with these two kinds of systems. So now a summary of our product, which permits to measure BSDF. The two first ones, MiniDiff V2 and MiniDiff V Pro, are based on camera, and the two other ones, reflect and high specular, are based on our gonio-photometer. If we take a look to the dynamic, the dynamic is higher for gonio-photometers than for camera-based system. Indeed, we are around 10 power 5 for MiniDiff V2 and MiniDiff V Pro, whereas we have 10 power 9 for reflect and 10 power 13 for the high specular. Regarding the angular accuracy, which corresponds to how close from the specular we are able to detect scattering, we have 1 degree for mini-G V2, 0.5 degree for mini-G V-Pro. For reflect, we are inferior to 0.1 degree, and for the high specular, inferior to 0.02 degree. A big difference is in the facility to use. You just have to see the way to understand. For mini-G V-Pro and mini-G V2, these devices can be sold, whereas for the high specular bench, we only propose measurement services in our lab. For reflect, it can be both, it can be sold, but we also propose measurement services in our lab. So now let's go to the core of the subject, retroreflection. Let's start with a short definition. Contrary to reflection, where the light is reflected with the same angle as the angle of incidence, retroreflection corresponds to a return of the light to its source. In optics, it's really a challenge to measure it, and it's, in fact, it could be very interesting and important to be able to measure retroreflection. Where can we find it, and why is it important to measure it? First example is on road sign and marking. In fact, retroreflection is a physical phenomenon that allows signs to remain visible at night. It's simply the ability of a sign or of a mark to reflect the headlight of an approaching vehicle, which is represented here. Signs and marking are composed of retroreflective paint, which are composed of glass microbead here, which permits to deviate the incident light and send it back in the same direction as the incident light. This kind of paints are mandatory for all categories of sign or mark. So you can easily understand that it's very essential to control and ensure the good quality of retroreflection to ensure safety. So it's important to be able to measure it, of course. Another example where retroreflection is very important is for LIDAR application. LIDAR is for light detection and wrangling. This kind of system uses light as a means for detecting objects and determining the distance, similar to the way as radar uses radio waves. In fact, it targets an object with an infrared laser and measures the time for the retroreflected light to return to the receiver. Applications for LIDAR system include, for example, topography mapping, 3D architectural site mapping, atmospheric studies, environmental studies, robotic vision, or autonomous vehicles. And with the rapid development of autonomous vehicles comes a need to develop efficient, reliable, cost-effective vehicle-mounted LIDAR systems. LIDAR system will likely be one of several detector types that can be used to build a dynamic 3D picture of the environment surrounding the vehicle. So I just present two examples of why it would be interesting and important to measure retroreflection, but there are lots of others. But how can we measure retroreflection? I explained that there is two ways to measure BLDF. First, with goniophotometer. You can see that with goniophotometer, in the retroreflection configuration, in fact, the detector hides the source. So it's clearly impossible to measure retroreflected light with a classical goniophotometer. However, with our camera-based system mini-G V2, thanks to an optical system, it's possible to measure retroreflected light. Here you have the source, and this system of lens permits to collect and send to the camera all the scattered light, even the retroreflected. So now I am going to present our mini-diff V2. Let's start with a short introduction. So it's a camera-based system. It's a portable device, fast and easy to use, which allows to obtain a 3D BSDF in one shot, thanks to a patented optical system. It is developed and assigned by Synopsys. It also permits to export measured data to simulation software, such as light tools, for example. And it also provides an integrating fitting tools for other export types. So now the principle, let's start with the BRGF measurement, because today we are interested in the reflected space. So the light is emitted from the mini-diff. The source is integrated to the mini-diff here. So it illuminates the sample. The sample scattered the light in many directions. The mini-diff optic collects all the light and send it to the camera to obtain a BSDF images. After a computer post-processing, we obtain the count. This step of post-processing contains, among other things, a step of straight light reduction to take into account the fact that the source are integrated in the mini-diff. For BTDF now, the principle is quite the same. The only difference is that the light is not emitted from the mini-diff, but from an external module here. But apart from that, it's the same. The sample scatters the light, the optic collect and send to the camera to obtain BSDF images. And after post-processing, we obtain the count. So now some technical specification. Regarding the source, we have one version visible of our mini-diff, and we have two versions of infrared. For the visible version, there are three LED light sources, red, green, and blue, which permits to obtain BSDF measurement for each color and to provide a global color estimate in LAB space using the TIS calculation from the BSDF measurement for each color. The software can show you the RGB 3D BSDF, which is represented here with this blue sample. Here you have the color RGB representation. So you can clearly have information on color. So now for infrared version, so as I said, it exists two versions, one with a wavelength of 850 nanometer and the other one 940 nanometer. So the principle is really the same, but of course you will lose information on color. Regarding angle of incidence, for BTDF and BRGF, you can have 4 angle of incidence. So for BRGF, 0, 20, 40, and 60 degrees, and you have the same corresponding angle for BTDF. So for the post-processing, your data has to be calibrated. So for that, you have to do a calibration with a measurement of a white reference, then a measurement of a black reference for all color and all angle of incidence you want to measure on your sample. The final BSDF value will consider your white reference, your black reference, but also the white reference characterized with our reflect bench. Of course, this value is already integrated in the software. You don't have to do nothing. But why is it important to take this into account? If you take a look here with the measurement of a white reference with our reflect, with different angle of incidence, you can see that it's in fact not perfect. We have a specular behavior for high angle of incidence. It's totally normal, but we have to take this into account. That's why we have this value. So regarding the time of measurement, you have to know that one measurement takes around 10 seconds for one angle of incidence and one color. So for a full BSDF RGB calibration plus the measurement, it will take you around 6 minutes plus 4 minutes. For a full BRGF RGB calibration plus the measurement, it will take you around 4 minutes plus 2 minutes. And for a full BTDF RGB calibration plus measurement, it will take you 2 plus 2 minutes. Of course, you can select which angle of incidence and wavelength you want to calibrate and measure. It is represented here. Regarding the stability, you have to know that it's important to connect the system at least 30 minutes before using it. It's just the times for all elements to be stable. We really advise you to do the measurement just after calibration, but if for some reason you can't, it's possible to do that even 1 hour after the calibration. It is represented here with one measurement every 5 minutes after the calibration. You can see that the stability is really maintained because it's around plus or minus 7% after 1 hour after calibration. So regarding the dynamics, thanks to a straight light compensation and an AGR algorithm for picture acquisition and other things, but thanks to these two things, we can have a dynamic range of 10 power 5. It's possible to calculate the TIS from the BSDF measurements. Here you have an example with this black anode, which have a reflectance of 95%. Here you have the TIS calculated from the BSDF measurement with the mini DV2, and it's about 94.9%. So it's a really good result. So regarding the MiniDiff software, it works with the MiniDiff V2 and the MiniDiff vPro. You have different extrapolation possibility. So for example, so here it's with a measurement without any extrapolation. Here you have a linear extrapolation, a Bézier extrapolation here, and a uniform extrapolation here. You can have different card types, BRGF, ARS, color, and RGB plot. Of course, available only if the RGB measurement is done. You also have a cross-section in a 3D card here, which can be manually shifted. I will show you this later directly in the software. It also provide different analysis tool to do some averaging, BSDF comparison, or parametric evaluator. As explained before, it permits to export the data for optical software such as light tools. And you have to know that it's a unique file exported for full measurement. So for a measurement with several angle of incidence or color, you will have only one file. So to recap some specifications, the field of view is around plus or minus 75 degrees. The repeatability 2%, accuracy 5%, dynamic 10 power 5, angular accuracy 1 degree, and color accuracy 20. So now I'm going to present you some measurement example. So first, a car bumper in infrared. I choose to show you this example because it's very interesting for LIDAR. As explained before, LIDAR use retroreflection to map the surrounding of a car, and a car bumper is an element often present on the surrounding of a vehicle. We choose to work, of course, in infrared, like LIDAR, so with the version 940 nanometer. We perform the measurement for all angle of incidence in the reflected space. Here are the results. I just present the result for the angle of incidence of 20 degrees. You have a perspective view here, and here it's the BSDF value scale. So as we light at 20 degrees, we expect to have the reflected light at 20 degrees and the retroreflected light at minus 20. So at 20 degrees, here we have a specular peak, and around this peak, we have a specular Lambertian background. And at minus 20, so where we have retroreflected light, we can detect this Lambertian behavior. So we are clearly able to measure retroreflected light. So now an example a little bit different, because we measure a sample without retroreflection. Since the beginning, I talk about materials detectable by LIDAR, but you can be interested in material undetectable by LIDAR for military application, for example. So we measure a mirror, which by definition reflects the light it receives in a specular way without retroreflection. We again use our infrared mini GV2 and with all the angle of incidence in the reflected space. Here are the results. So we use the cross section here, and we can see that at 20 degrees we have the reflected peak, and we have nothing at minus 20 degrees. So this mirror won't be detectable by LIDAR. So as explained at the beginning, so we have for retroreflection application the LIDAR, and the other one was for road sign and marking. So I want to show you an example of road sign measurement. We choose a stop sign. We perform a measurement on the red part and on the white part of the sign with our visible mini DV2. So with the red, green, and blue, and for all angle of incidence. So first, the result for the white part of the sign, represented here with an angle of incidence of 20 degrees, and for the green color, for example. You can see, so it's a retroreflective paint, of course. You can see that at 20 degrees, so in the reflected part, we have a small specular peak, and at minus 20 degrees, we have a really higher peak for the retroreflected part. So we are clearly able to measure the retroreflection. If we take a look here in 2D representation with the other color, red, green, and blue, we have the same observation. It's not very interesting here because it's in the white part, so it's more interesting to look this representation with the measurement in the red part of the sign, and you can clearly see that the red curve is higher than the other one. So we have really an information on color thanks to the mini GV2 measurement. I'm going to show you this in the software. Okay. So we are in the red part of the sign here. So I choose a perspective view, the cross section here, which can be manually shifted. So let's go to T minus T, where we have the retroreflection. Here you can choose the representation you want, so BSDF, ARS. So let's start with BSDF. Here you can choose the angle of incidence. So for example, 20. And here you can choose the color. So for blue, for example, the retroreflection is really lower than for red, green, a small peak here. And in red, the peak is really higher. So you clearly have the information on color. Here you have the estimation of the teeth. So now let's take a look to the RGB representation. You have a red dot, so you have the information on color. Let's go back to the presentation. So to conclude with this measurements, we have seen that the Mini V2 is able to measure retroreflected light, of course, and to quantify BSDF, which permit to qualify, for example, the visibility of a sign, or to see if an element will be detectable or not by a LIDAR. And we have also seen that thanks to RGB measurements, the color appearance of an object can be obtained. As I explained before, all this data can be exported for optical software, such as Light Tool. That's why I'm going to present you some Light Tool simulation done from measurements. We are going to compare the stop sign with the surface property extracted from the stop measurements to the same sign with a standard non-reflective paint. Both signs are illuminated by a car at a distance of 50 meters, and we are going to calculate the luminance map from the driver position. Here are the results. So you have here the stop sign with the retroreflective paint, and here the stop sign with a classical paint. Here you have the luminance map and the representation in color. Yeah. The retroreflective level is higher for the measured sign than for the one with conventional paint. The brightness of the sign from the driver position is enhanced by the use of a retroreflective paint, of course. So the driver will therefore see the sign better with this kind of paint. In addition, on the retroreflective simulation result, we can clearly distinguish the retroreflective lobe effect compared with the regular diffuse component of that. So we are able to study the visibility of the sign. We can imagine that we can change the distance or the position of the driver or other things. So to conclude, we have seen that measuring retroreflection is very important in lots of fields, for example, LIDAR or road sign and marking. But it's really a challenge because it's impossible with classical goniophotometer. Our solution for that is our camera-based system, INIDIF V2, and which, thanks to an optical system, allow to measure the retroreflection. In addition, the software permits a clear and easy representation of the data, and permit to export our data to optical software. Thank you.